Hello, my name is Jorge Muñoz, and today I'm going to be talking about the James Webb Space Telescope. The James Webb Space Telescope is an orbiting infrared observatory developed by NASA with collaborations from the European Space Agency and the Canadian Space Agency. It is named after James Webb, who was the NASA administrator from 1961 to 1969 during the Mercury, Gemini, and Apollo programs, and he established research as one of the main activities of NASA. This telescope was proposed in 1989 during the Next Generation Telescope workshop at the Space Telescope Science Institute. This is the first concept here. And in 2002, the contract was awarded to TRW, or Northrop Grumman now, to design the spacecraft pass, and to Ball Aerospace to design the observatory itself. In December 25th, 2021, the James Webb Space Telescope was launched into orbit aboard an Ariane 5 rocket from Europe Spaceport in French Guiana. Originally, the mission was going to last 10 years. However, thanks to the need for a few mid-course corrections, it was possible to double it to 20 years. The reason why the few mid-course corrections was important is because the amount of propellant stored in the spacecraft is really what determines the length of the mission, as it is used to adjust its orbit. Now let's talk a bit about the science goals of this mission. The first one is to study the reionization and first light periods, which happened about 13.5 billion years ago, 300 million years after the Big Bang. This epoch is characterized by the formation of the fresh stars, 30 to 300 times more massive than our Sun. These stars emit very strong UV radiation, which ionize the hydrogen atoms surrounding them. According to Einstein's general relativity, the expansion of the universe also caused the light to stretch, meaning that the UV light that was emitted by these early stars reaches us now in the near-infrared spectrum. That's why an infrared observatory is needed to take a look at them, to do science with them. We also want to study how the small and clumpy galaxies that form in the beginning of the Big Bang became these massive spiral galaxies that we have right now. Here we can see some of these galaxies that I'm mentioning seen by the Hubble Space Telescope. This is just a render of a modern spiral galaxy, which, as you can see, is much more complex. We also want to understand how stars are created and how protoplanetary systems come about. These type of systems are normally created inside dust clouds, where there's a lot of matter which just clump into stars. These dust clouds are opaque to the visible spectrum, however, they are fairly transparent to the infrared one. Here you can see the pillars of creation. The one on the left is a picture taken by Hubble in the visible spectrum, and the one on the right is the same picture in the infrared, and is also taken by Hubble. We also want to study the exoplanet's atmosphere and understand it better by using the onboard spectroscope that is inside the James Webb. This type of spectroscopy basically allows us to see the absorption of the molecules in the atmosphere of the planet, and it can tell us whether that planet has a habitable atmosphere or not. Now, why do we need an orbiting infrared observatory? Wouldn't it be cheaper to produce it, to make it on Earth, to build it on Earth? Well, there's two main reasons why we need an infrared observatory on space. First of all is that if we want to look at potentially habitable exoplanets, we have to take into account that the same molecules that are in their atmosphere are the molecules that are in the atmosphere of the Earth, meaning that the absorption of the light can be due to the molecules in our planet or the molecules in the exoplanet we're looking at. There's a way to get around this and actually see which planet is doing the absorption, which atmosphere is doing the absorption. However, it's much easier if we set the observatory in space. The second reason, and probably the most important reason why we need to have an orbiting infrared observatory, is to look at the mid-infrared radiation. As we know from Planck's law, every object which is above 0 Kelvin emits radiation. Now, it turns out that the Earth emits radiation right in the mid-infrared region, from 6 to 28 micrometers. This means that any infrared telescope which observes in the mid-infrared region would be basically blind by the radiation of the Earth. That's why we need to put it outside the Earth and actually shield it from the radiation from Earth, which I will be talking about later, how the James Webb performs that duty, that task. Now let's take a look at the orbit of the James Webb Space Telescope. The James Webb Space Telescope orbits around the Lagrange 2 point, in contrast with Hubble, which orbits only 570 kilometers away from Earth. This is 1.5 million kilometers away from Earth, the Lagrange 2 point. This is a metastable point in the Earth-Sun system, and it allows the telescope to rotate at the same speed as the Earth, which means that it never gets blocked by the shadow of the Earth or the Moon. It has easy communication with the Earth, and there's a constant power supply from the Sun. And also, it's much easier to cool the telescope since you only need to block the Sun's light from one side, which is what the Sun shield does. Now let's look at the specifications and what makes up the James Webb Space Telescope. So we have the spacecraft bus, which is basically the backbone, contains the electrical system, attitude control, communications, and the cryocooler used to cool down the MRI camera, which I will be talking about later. This is a mock-up, and this is just a couple of pictures, a couple of drawings. Now the sun shield is probably one of the most interesting parts of the telescope. It's made out of 5 thin layers of polyamide coated with aluminum with ripstop seaming, which basically just ensures that when a micrometeorite hits the sun shield, the rip doesn't extend through all the shield and reduces the effectiveness. As you can see here, it keeps the cool side of the telescope at about 40 Kelvin, and it does so by basically just reflecting the sunlight. It's the 5 layers reflect the heat back to the sun. The 2 first ones are doped with silicon to improve the reflectivity, and the reason why there are 5 is a mixture of redundancy and also just it makes it much more efficient at actually cooling down the telescope. The optical elements inside the telescope are 3 mirrors and a 4th fine steering mirror. The 3 mirrors make an astigmat configuration, which is basically just a type of telescope which reduces the astigmatism, and spherical aberration. Here we can see it. And basically, the most interesting part of this system that I've described before is the primary mirror, which is made out of 18 mirror segments. The whole mirror is 6.5 meters in diameter, and the segments are hexagonal. This means that the packing factor is very high, but it's actually 1. You can see there's no seams between them. And also it has another bonus, the fact that the shape of the mirror, the primary mirror, is hexagonal, and that is the symmetry. As you can see, there are only 3 different types of mirrors that had to be produced. Each mirror segment is made out of beryllium. It has a diameter of 1.32 meters, and the reason why it's made of this metal is because beryllium is light and resistant, and also has a very important characteristic, which is low thermal expansion. A gold coating improves its reflectivity, and 7 actuators control its position. 6 of them are set up in an hexapod configuration to control the attitude and position, while a 7th one controls the curvature of the mirror. The whole assembly comes out to weight about 40 kilograms. Here we can see the drawing. Now, one thing that you will see from the images in the James Webb Space Telescope that might seem a bit weird is these 6 spikes. Of course, we know that stars don't have 6 spikes, and you probably are used to seeing stars with 4 spikes. Those spikes there are called diffraction spikes and are caused by the struts holding the secondary mirror in a reflector assembly, such as the Hubble. If you look at a picture from the Hubble, I have shown a couple before, and you see these diffraction spikes pretty well. The reason for these 6 diffraction spikes, however, is not the struts that hold the secondary mirror, but rather the aperture. We know when a plane wave passes through an aperture, some diffraction is created, and that's what is appearing here, a diffraction pattern. You can see these 2 small spikes here. Those are actually caused by the struts holding the secondary mirror. So if you want to tell apart the James Webb Space Telescope images from the Hubble Space Telescope, you just have to look for these 6 peaks, and that's a pretty easy way to tell them apart. Now let's talk a bit about the cameras inside the telescope. We have the NRR camera, which covers the near-infrared range from 0.6 to 5 microns in wavelength. It is used to image galaxies nearby as well as stars inside our galaxy. It also includes a coronagraph, which is an instrument used to observe faint objects near bright ones. It basically block the bright object, allowing us to see the fainter one. This camera also contains the wavefront sensor, which is used to align the mirrors in the primary sensor. Here we can see a picture of the assembly, and this is the most interesting graph. It basically shows you the different regions in which James Webb operates. Have the mid-infrared here with the MRI, and then all these near-infrared spectrometers and camera. This is also a spectrometer and camera, are used as their name implies in the near-infrared. Now let's talk about the near-infrared spectrograph. This is basically used again to observe nearby galaxies and look at the composition of the exoplanets' atmospheres. The main innovation is a microshutter which allows to record 100 spectra simultaneously, and actually they are controlled. This is the microshutter, and it's controlled by magnetic fields. So that's the main innovation in this instrument. Now we have the mid-infrared instrument, which is probably one of the most interesting ones. This allows the James Webb to look at objects in the range of 5 to 18 micron range, which produce radiation in the range of 5 to 28 microns. This wavelength sensitivity means that the system needs to be cooled down to 7 Kelvin. As I said before, Planck's law comes into play here. We need to remove the thermal noise. That 7 Kelvin, by the way, is just the actual imaging sensor. The rest of the system works just as at the 40 Kelvin that the whole observatory works at. It can also perform spectroscopy, and it will use to look at fainter stars, galaxies, and Kuiper belt objects, which is the belt around Pluto, I mean. Now we have the fine guidance sensor and the near-infrared imager and slitless spectrograph. It's mainly used to guide the telescope, but it will also be used to observe the first light and perform some spectroscopy of exoplanets' atmosphere. As you know, the James Webb Space Telescope is actually folded to fit in the Ariane 5 fairing, and once it was launched, the 25th, it took it about 2 weeks to fully unfold the 8th of January. Now let's look at the mirror alignment. This is one of the most interesting parts, and it's the first time that this type of operation has been done in space, since this is the first telescope which has a segmented mirror. So the first thing we do is we take a picture, then we wiggle each segment of the mirror individually and look at the image it produced. By the way, this is the same star, just 18 images, one for each mirror. Here we can see that we get three images corresponding to the wings, and then 12 corresponding to the segments in the center. Now, once they have been identified, they are arranged in this grid pattern and they are focused. After that, the images are stacked together, and we get these first images, this first image, which is just the 18 images superimposed. This is just as if we were using a 1.32 meter telescope. Now we need to adjust their faces so that we have an actual 6.5 meter telescope. This is done with the coarse facing and the fine facing. In the coarse facing, we use a Sachs-Hartmann wavefront sensor to find the piston error. This sensor basically just has an array of lenses in front, a focal length away from the CMOS sensor, and the pattern created can give you an idea of the wavefront shape, which again gives you an idea of how the mirrors are aligned. Then the fine facing is done using an algorithm and different types of images from different out of focus secondary positions. This is repeated 3 times, and then it leads us to the iterative alignment. The iterative alignment is the last stage of alignment for the final for the primary mirror, and it leads you to the final images. You can follow the progress of this alignment, which is the stage at which James Webb is right now in this web page, and you can also look at some of the sources that I use. if you're interested in learning more about the JWST. So I just want to thank you for your attention, and yeah, thank you very much, and I will be answering whatever questions you have now.